Look closely at this image of the Golden Gate Bridge during rush hour. You're seeing thousands of vehicles packed bumper to bumper, adding millions of pounds of active, moving weight to a steel structure that already carries a dead weight of nearly 900,000 tons. It is an incomprehensible amount of metal, concrete, and humanity suspended directly in thin air. And yet, this massive corridor doesn't plunge into the dark water below. The biggest threat to a structure this size isn't wind, earthquakes, or cars. It is gravity relentlessly pulling down on its colossal dead weight. Engineers know they cannot defeat gravity. Instead, they have to manipulate it. They designed elaborate structural funnels to gather that crushing weight and dictate exactly where it is allowed to travel. A bridge of this scale is a highly efficient, active machine, constantly managing an unseen war of kinetic energy. Check out this aerial view showing a dense crowd covering the bridge deck. The sheer downward pressure from the road alone is immense. If you built a simple, flat beam across a gap this wide, it would snap under its own mass in seconds. To stop the deck from breaking, it is caught by a series of vertical suspender cables that act as an immediate failsafe. These ropes introduce our first physical rule: tension. As gravity tries to drag the roadway down, these cables pull back, fighting the descent by stretching tight. Look at this close-up of construction workers wrapping these thick bundles. Because they are spun from thousands of individual strands of steel, these cables can endure immense, continuous pulling force without failing. But those vertical suspenders can't hold the bridge up by themselves. They act as intermediaries, transferring all that tension higher up into the massive main cables. By catching the road from above, the architecture converts the dangerous downward deadweight of the asphalt into a highly controlled upward pulling force. You can see exactly where that upward pull goes in this high-angle shot looking down the main cords. They drape in a sweeping geometry, acting like a giant steel hammock that gathers the cumulative weight of the entire structure. That gathered weight travels the length of these cables, climbing higher and higher until it reaches the very apex of the vertical towers. Right at the top, the physics flip completely. The draped cables stop pulling up and instead press heavily into the crown of the towers. This is our second physical rule: compression. The pulling force of tension has just been transformed into a violent squeezing downward pressure. To survive being crushed from above, these towers are designed with extreme rigidity, built out of interlocking steel plates designed specifically to absorb that squeeze. Take a look at this wide shot of a single tower standing in the water. It routes all that compressive force down its colossal legs and safely buries it deep into the solid bedrock beneath the ocean floor. By taking millions of tons squarely on their shoulders, the towers act as the ultimate gravity funnels, saving the suspended roadway from certain collapse. There is still one major vulnerability. The main cables are holding millions of tons of tension. So why don't the ends of those cables simply whip loose and rip the bridge apart? They are pinned in place by massive blocks of concrete called anchorages, buried deep within the shorelines on either side of the water. This animated diagram tracks the complete active path of force. Watch how the arrows pull up from the deck, travel along the main cables, push straight down the towers, and finally pull back at the shores. The anchorages act as a terminal counterweight. They drag backward against the main cables, pound for pound, to equalize the math. By balancing tension pulling one way against compression pushing the other, the structure locks itself into a rigid, immovable state of equilibrium. A giant suspension bridge is an optical illusion, hiding a furious, active transfer of energy behind a facade of stillness. Every single ounce of weight is caught in tension, passed upward to the main cables, transferred into the towers as compression, and escorted safely into the earth. So the next time you are driving across a span like this, suspended hundreds of feet above the water, take a second to look up at the massive steel ropes and towering pillars surrounding you. A perfectly balanced web of physics cradles every traveler crossing these waters, marking one of humanity's greatest mechanical achievements.